This video is going to talk about solutions, saturation, and solubility, and what exactly those things are, because they all start with the S. So the good news is they all go together. We're going to talk about the parts of a solution. So we're going to talk about solution first, and then after that, we're going to talk about saturation. There's 3 types of saturation you need to know. And then after saturation, we're going to talk about solubility in this section. And then lastly, we're going to talk about how to quantify saturation. So let's jump in with the parts of a solution, which we briefly introduced to you earlier in this level. So there are 2 main parts of a solution. Part number 1 is the solute, and part number 2 is the solvent. So let's use an example. So here's my example, NaClAq. You remember from balancing chemical reactions that this AQ stands for aqueous. And aqueous sounds like aqua, which means water. So really this AQ, which stands for aqueous, tells us that something is dissolved in water. And what is dissolved in water? That's going to be what comes before the AQ. So we have NaClAq. NaCl is sodium chloride, good old table salt, and that has been dissolved in water. So let's show that in our, we'll call that a beaker next to it. So let's say we want to make a solution of salt water, NaClAq. Well, we need some salt and we need some water. So let's say we pour in some water. We've got our water. And then we put in some salt. I'll use some gray dots for the salt. So these are our 2 parts of the solution. Now, obviously, once this is dissolved, we cannot see the salt anymore. But our 2 parts here, the water, that is going to be our solvent. So looking at our example here, water is our solvent. And then our solute is going to be NaCl. So water is our solvent and NaCl is the solute. So here's how I recommend remembering them. Solute is what you add to the solution, and the solvent is what is going to dissolve then. So the solute is technically what dissolves in a solution, and then a solvent is what does the dissolving. So what is going to be dissolving the solute? So the solute, you add that to the solution. So you add the solute to the solvent. So these 2 things together, the solute and the solvent, when we put them together, that equals a solution. So those 2 things together are the solution. Now, when it comes to solvents, there is something called the universal solvent, and the universal solvent is water, which is great at dissolving all sorts of things. So water is known as our universal solvent, but it's not the only one. There are all sorts of other solvents that we could have, and they could be different phases of matter too. But most of the time, what you will encounter will be water as your solvent. So those are the parts of the solution. So let's talk about now saturation. So think if something is really saturated. There's gonna be a lot of it, right? So when we're looking at saturation, we're gonna be looking at how much solute is in a solution. And when we're talking about saturation, you can kind of think about it like Goldilocks and the 3 bears. There's the porridge that's too cold, or the bed that's, too soft, and the bed that's too hard, and then there's one that's just right, and the porridge is the right temperature, right? So it's sort of like Goldilocks and the 3 bears here. So saturation, we have unsaturated, then we have saturated, and lastly, we have supersaturated. So we're going to start with supersaturated and work our way backward. Let's say we have that solution of salt water again, so aqueous sodium chloride here, and we have a beaker and it's full of water, so we'll say the blue stuff is water. And then let's say we pour in so much salt, and I know I'm using gray and salt is white, but anyways, say you pour in so much salt that it starts to pile up at the bottom. This would be a super saturated solution because this is so saturated with salt, it can't dissolve anymore. So that would be a super saturated solution when we have more solute than can dissolve. We'll write down definitions in a moment. Now let's go to the other end of the spectrum. Let's say we have an unsaturated solution. An unsaturated solution would be like, we're gonna add just a little bit of salt, just a little bit, and it dissolves and it goes away. But it's really, really weak when it comes to that sodium chloride concentration. Now, obviously we don't taste anything in lab or with that, but let's say hypothetically you were to drink these, right? Let's say you had this beaker of water and just a little bit of salt. It's really unsaturated. You could drink it and you wouldn't even know there was salt in it. that would be an unsaturated solution. And then we have a saturated solution. And a saturated solution is the most solute we can put in there that still dissolves. So anytime you start seeing things collect on the bottom, that means you have a supersaturated solution. But if we have just enough in there, and obviously we wouldn't be able to see these because they would dissolve, if we have enough in there that it's still floating around and able to dissolve, now we have a perfectly saturated solution. We have the maximum salt we can put in there and it still dissolves. So let's write down some definitions. So let's start with supersaturated. So supersaturated solution would be there's more solute than a solution can dissolve. A saturated solution then is the maximum amount of solute that we can put in that can dissolve. So this is the maximum that we can put in that still dissolves. The moment we put in more than can dissolve, now we would have a supersaturated solution. And then an unsaturated is less than the maximum amount that can dissolve. Right, so unsaturated, you taste the salt water, it's super weak. Saturated, tastes salty because it's the maximum amount that can go in there. And then super saturated is like there's salt on the bottom and it tastes gross. So those are our different types of saturation. So when we are pouring that salt in the water, we want it to dissolve really well. So let's think of some things that we can do to make the solutes dissolve better. So AKA, let's use some vocab here. How can we increase solubility? So when you hear the words soluble or solubility, I want you to think of the word dissolve. So dissolve and solubility go together. So how can we increase solubility? How can we make something dissolve better? So there are some different ways to do this. Number one is we can just stir it. And this is our gut reaction as we just start stirring things. You add sugar to your tea, you start stirring it. That's a way to increase solubility. Let's say you're adding sugar to tea and you have a giant not salt cube, we don't add salt to tea. You have a giant sugar cube compared to some really small, like powdered sugar, really fine. You can think about which one would dissolve better. Would it be a giant sugar cube or some powdered sugar? It's going to be the powdered sugar, and that's because the particle size is already smaller. So a smaller solute particle size will dissolve better and will increase solubility compared to a large one. So think sugar cube compared to powdered sugar. And the last one is that we can add heat. So if you warm up a solution, you are increasing the distance between particles, and that creates more space for the solutes to insert themselves. Okay, so those are ways that we can increase solubility. Now, let's look at a solubility or saturation graph. So this is called a solubility curve, and I don't expect you to draw this out on your notes. However, what I do expect you to draw is something that looks like this. Give us a quick X and Y with temperature down here, and then grams of solute on this side. So we're not going to have you draw the whole thing out, but I do want you to have a general look at a solubility curve. And then you're welcome to just draw any sort of line on there that looks like that. So let's talk about this. And then you can label yours and I'll show you what it looks like when it's labeled. This is a solubility curve and it looks like a mess because there's so much on it. So whenever you see a solubility curve, which I've seen on ACTs before, just keep that in the back of your mind. You're just going to pick out one thing to look at. So we're going to pick out potassium nitrate, which is here in the middle and kind of looks similar to the line that we've drawn there. So we're going to call this line KNO3 on your notes. So we're only going to look at this line, and I'm going to make this line darker so that it's easier to see on here. So this line represents saturation. So this is the line that means perfectly saturated. So this solubility curve is really a saturation curve. So this is the perfect amount of what can dissolve. So we could get coordinates from here, just like we could from a regular graph in math, and we could say, okay, right here, at this point, if we have a solution that is 50 degrees Celsius and 100 grams of water, it could dissolve 80 grams of KNO3, and it would be the perfect maximum amount that we could dissolve it. That's how we would read that line. Now, let's say we had another point. Let's say we were looking at this point here, which is 40 degrees Celsius and 90 grams of solute. This is to the left of the line. So this point is to the left of that line. Anything that is to the left of the line represents a supersaturated solution. So this would be supersaturated here. Now there's lots of supersaturated points, right? We have an infinite amount of points here on that side of the graph. So what we need to know then is this line represents saturated, then anything to the left in this green section, this is supersaturated. So that would represent supersaturated. Now let's talk about below the line. Let's say we have a point below the line for KNO3. Let's stick with our 90 grams of solute, but let's say now we increase the temperature to 70. So now our temperature is at 70, but we still have the 90 grams. This is now going to be an unsaturated solution because we are below the line. So we are to the right of the line now with this point. So we're to the right. So this is going to be an unsaturated solution. So anything to the right of that curve is an unsaturated solution. So this blue section represents unsaturated. So that's generally what we're looking at with a solubility curve. Now remember, this will change based upon which substance you are looking at. So we use the KNO3 line here. All right, let's keep going with our conversation about saturation. And let's talk about how we can quantify saturation because, you know, in science, we love to just quantify everything. So there are multiple ways to quantify saturation. Here's one, and it is called molarity. And if you're thinking, wow, molarity, that really sounds like the word mole that we learned about last unit, you would be correct. Those things go together. So the unit for molarity is represented with a big M, and molarity is equal to the moles of solute divided by the liters of solution. So for our units, we have molarity, which is a big M. Moles, we just write moles, and then liters, we have an L. So those are our units. So this is a way to quantify saturation. So let's say we have two different solutions, and let's say our two solutions are both hydrochloric acid mixed in some water. And we have one solution that has a molarity of 1, and we have one hydrochloric acid that has a molarity of 4. Let's think about which one would be a stronger saturation of our solute, hydrochloric acid, HCl. Well, 4 is a lot higher than 1, so 4 would be a higher concentration, and then 1 would be a lower concentration. So molarity is a way for us to quantify this. We're gonna do a couple example problems together. Here's the first one. It says, if there are 7 moles of calcium chloride, CaCl2, and 3 liters of water, what is the molarity? So we are going to solve this together. So we know our equation for molarity here is moles divided by liters. And this is really just a plug and chug problem. We're gonna find what we need and then swap it in there. So we are looking for molarity, and we know that is equal to moles of solute divided by liters of solution. So let's fill this in. So the problem says there are 7 moles of CaCl2. So looking here, 7 moles of solute. So let's fill in this information. Our solute is CaCl2, and we have 7 moles. And then it says in 3 liters of water, and we have liters of solution, which would be water. And we're just gonna put 3 on the bottom. And then all we have to do is put that in our calculator, 7 divided by 3. So if you type in 7 divided by 3 in your calculator, you get an answer of 2.3. We also need to put our unit for molarity, which is just a big M. And that's it, that's really not bad. There's all sorts of different variations we could do with this mathematically. We could solve for molarity, we could solve for moles, we could solve for liters. So we're gonna do one more like this, and then you'll do more practice later. A solution has a molarity of 2.3. How many moles of the solute are needed if the solution is 0.6 liters? So go ahead and see what you can set up. So go ahead and pause the video, try to set this one up, and then we'll go over it together. So go ahead and pause the video. All right, let's go over this problem. So when we are reading, it says molarity is 2.3, which means we're gonna sub in 2.3 right here. And then it says how many moles. So we're looking for moles. So we're gonna put an X there because that's what we're solving for. You could use any variable or leave it blank, however you wanna do your algebra is fine. And then it says if the solution is 0.6, that's supposed to be a highlighter. If this is 0.6 liters, which means 0.6 is gonna go down here with liters. And the last thing we do then is we need to do our algebra. So in order to get x by itself, we're going to multiply 2.3 by 0.6. And when we do that, we get 1.38, which means our answer, well, you can leave it like that, or if you want to round, you can. It would be 1.38 moles of solute. And it doesn't say what the solute is, but that's okay. Alrighty, so that is it in terms of the basic problems. Now, if you are in honors, you are gonna watch this next section, or if you are just wanting to know the next section, you are welcome to as well. However, if you are in a CP class, you can stop here. Honors, you need to watch one more type of problem, but like I said, if you're in a CP class and you're like, I just wanna watch the next problem, go for it. All right, here is our extension for this, and it's a little bit more difficult because we're gonna incorporate some mole conversions. So go ahead and look at the problem. The problem says a student wants to make an aqueous solution of NaHCO3, which is baking soda. The molarity needs to be 3.4 and it has to be 1.5 liters. So how many grams of solute will the student need? So at first glance at this problem and looking at what we know about the molarity equation, we run into a problem, right? We're looking for grams. There's no grams on here. That's a problem. However, you guys and your awesome chemistry knowledge know that you can convert from moles to grams using molar mass. So that's what we're gonna have to do with this problem then. So the first thing that we need to do is figure out moles on its own. And then once you have moles, you need to convert using the molar mass to grams, so using some dimensional analysis. So go ahead and solve for moles of solute, and then we will set up the mole to gram conversion together. But go ahead and pause the video and solve for moles. When you solved for moles, your setup looked like this, and you got an answer of 5.1 moles. And you might have also substituted out the word solute for NaHCO3. And if not, we know that our solute is going to be NaHCO3, so we can jot that down instead. So now what we need to do is convert this to grams. So this becomes our given when we do our gram conversion. So we start with that, we put it over 1, and then we convert to grams. We have moles NaHCO3 up here, so we pop that unit down here. And then we are converting to grams. We're gonna use the molar mass, and we're gonna fill that in here. So go ahead and calculate the molar mass of NaHCO3 and pop it here. So pause the video, calculate the molar mass of NaHCO3. Okay, for the molar mass, you got 84. And if you're like, whoa, where did we get 84 from? Really quick, off to the side, we have Na, there's one of them, has a mass of 23. H, there's one of them, has a mass of 1. And then carbon, there's one of them with a mass of 12, and oxygen, there's 3 with a mass of 16. And we get all those subtotals and we add them together and it's 84. So that's where the molar mass comes from. And then we're ready to solve our dimensional analysis because moles of NaHCO3 cancels, and we're just gonna take 5.1 times that 84, and you get an answer of 428.4. Now, if we were using sig figs, our answer would have 2 sig figs in it. So if you would like to do 2 sig figs instead, that would be 430. If not, we can leave that, and it would be grams of NaHCO3 for our final answer. All right, so that was our extension for honors, or if you just wanted a little extra challenge there. So sometimes we could also go to grams instead, because if you're making a solution in the lab, you're not gonna measure out moles on a balance, you're gonna measure out grams. So it's very practical to be able to go to grams. All right, that ends our video about solutions, saturation, and solubility.